Chapter 31, Faraday's Law of Induction. Take a look at this setup. I've got a battery over here, I have a switch, I have an iron core, and I have a coil, a primary coil wrapped around this iron core, and I have a secondary coil wrapped around the iron core as well, and the secondary coil is going to a galvanometer, so it's going through a meter to measure current. And what happens when I close the switch? Well, when I close the switch, a current will start to flow in this primary coil, and it'll set up a magnetic field like a solenoid through the center of that coil, and that magnetic field will be enhanced by the fact that we have an iron core. So the iron is going to make that magnetic field that much stronger due to the mu as opposed to mu naught. So I'll have a magnetic field. However, I'm going to notice something interesting here. When I close the switch, this secondary coil and the secondary meter is going to show a deflection, indicating that there is a current flowing in that second circuit. Now, iron itself is not a very good electrical conductor, so there is no electrical reason why this second current should flow. There's a magnetic reason. When I close this primary coil, there's going to be a magnetic flux, a change in magnetic flux. That change in magnetic flux is going to be felt by the secondary coil, and that is going to induce a current to flow, and hence we will see the deflection on the secondary meter. This secondary meter does not have a battery, so the only way that we can get a deflection is if a current has been induced to flow in that secondary coil. So this kind of experimental setup will show that an electric current can be induced by a changing magnetic field through this core. But it only happens when the magnetic field is changing. So when I close the switch, we'll see the deflection, but then once the switch is closed for a while, no more deflection. When I open the switch, it'll deflect the other way. So when I close the switch, deflects one way, open, deflects the other way, and I could keep on opening and closing the switch, and I could cause the deflection to go back and forth, induce a current back and forth, but only when I'm changing the circuit. Here's another example. I have another galvanometer, and I have it's hooked up to a coil, and I have a magnet. I'm going to move the magnet into that coil, and again, there's no battery in the meter, no battery in the galvanometer. So the only way that it's going to register a current is if I induce it somehow through the use of this magnet. And I'll find that when I move this magnet into the coil like this, I will indeed induce a current to flow, but only when I'm moving the magnet. When I stop, there will be no more deflection of the meter, and then when I pull the magnet away, it will deflect in the opposite direction. So only when I'm changing the magnetic flux through this coil do I get a deflection on the meter. I actually have this set up, so let's take a look at this. Here's our setup. We've got a coil up here. We have a meter down here. No battery to the meter. Here's a magnet. And when I move this magnet into this coil, it causes a deflection of the meter. If I just hold it there, no deflection. But if I pull it out, there's a deflection. So only when I'm moving this magnet one way or the other is there a deflection. Or if I move it gradually, I can get a deflection. But once a new status quo has been established, no more current. It's got to be a changing flux that will cause the current. Nature is opposing the change. That's what's causing the current. In other words, in this case, we're looking at this magnet right here with the north pole going towards the coil. I'm coming closer to that north pole, so as I'm coming closer to the North Pole, I'm getting closer to a more dense distribution of flux lines. Hence, the flux is getting stronger as that pole is approaching. Nature wants to oppose the increase in flux in one direction by creating its own flux, if possible, in the opposite direction in order to maintain the status quo. So, if it can, it'll do it. And if it can set up a flux in the opposite direction, that will require a current to flow through the coil to set up that magnetic field. And hence, that is the current that is flowing. It is opposing the change in flux in the first direction. So, we find the same thing that if I were to pull the magnet away, if I pull it away from that coil, then all of a sudden the flux, which is in this direction outside of the North Pole, is starting to decrease. Nature tries to keep things the way they were. It's trying to oppose the change. So it will set up its own magnetic field in the same direction as the original magnetic field to supplement so that things kind of remain the same. So as I'm pulling this away and weakening the flux in that direction, the current will be induced to create a flux in that direction, and that will be caused by current flowing in this coil, and we'll see the deflection on the meter. It's like anything interesting in science, it really doesn't happen unless you try to change something. If you're a biologist, you would talk about ecosystems, how ecosystems will remain the same forever and ever and ever unless you give it a drastic change on the ecosystem, and then all sorts of things start happening. In physics and chemistry, one example in physics is Newton's law of motion, first law of motion. An object at rest will remain at rest, or an object in motion will remain in motion unless acted on by a force. And when you see a change in that motion, then you know something interesting has happened. A force is there. And so it's the same thing in electrodynamics. When you change an electric field, you get a magnetic field. And here, when you're changing a magnetic field, you get an electric field. And in this case, an EMF being induced in this coil. So these results lead to Faraday's law. And it looks like this. The induced EMF, which would be a voltage, is equal to the negative number of turns that you have times the change in magnetic flux per time. So if you have a change in magnetic flux, you will induce an electric voltage. So a voltage EMF is induced if the flux changes. The N factor allows for more than one loop. And the negative sign by itself is called Lenz's law, and simply stating that the induced EMF is trying to oppose the change in flux, utilizing that property of nature of opposing change and trying to maintain the status quo. So that one little negative sign is what Lenz has got a law for, just the negative sign. And he probably just introduced the ideas of this EMF opposing the change in flux. We can see magnetic flux, like electric flux, is proportional to the total number of field lines that pass through an area, and in case of a wire loop, it would be the number of field lines that go through the wire loop. So if I had an orientation of a loop like this with the field lines going through, I would have maximum flux going through. But if I change the orientation this way, I would have zero flux going through, no lines going through that coil in that orientation. So I could increase the flux by increasing the magnetic field. And the way I would increase the magnetic field, at least represented, is by drawing more lines, and that would indicate a stronger magnetic field. So I would increase the flux by increasing the magnetic field. I could increase the flux by increasing the area, because then I would encompass more lines, presumably that if there's a magnetic field over here and here as well, then I would encompass more lines and increase the flux that way as well. Or if I were to change the angle of my loop, move this way, I would change the number of flux lines that would go through the loop, and I would change the flux that way. So there's three ways we can change the flux. Change the field, change the area, or change the orientation of the loop. If it were a planar loop, the flux would be given by our perpendicular field times the area times the cosine of the angle theta. And so, for instance, if theta were 90 degrees, then the flux lines would be perpendicular to the area vector and they'd never go through the loop, and you'd have a flux of 0. Whereas if the theta were 0 degrees, the field and the area would be in the same direction. All of those flux lines would go through that loop. So, using this result, our average voltage that could be induced in a circuit, in a loop, would be equal to the negative number of turns, the change in flux over the change in time, flux being for a planar loop like this, the field times the area times the cosine of the angle between the two vectors. So we would get an EMF, a voltage, if the magnetic field changed, if the area changed, or if the angle between the area and the magnetic field changed. We're going to be using this in the context of power very soon, and in most of our power generators we're using a large magnet so the field doesn't change, and we use one coil so the area doesn't change, but we're going to be moving the orientation of the coil, so if we change the angle of the coil, we will change the flux and induce a voltage, and hence a current. Any combination of these could induce a voltage, but that's the way we do it in the power plants, is we change the orientation of the coil. Let's try an example. A coil consists of 200 turns of wire having a total resistance of 2 ohms. Each turn is a square of side length 18 centimeters, and a uniform magnetic field directed perpendicular to the plane of the coil is turned on. If the field changes linearly from 0 to 0.5 Tesla in 0.8 seconds, what is the magnitude of the induced EMF in the coil while the field is changing? So here we have a square coil. We have 200 turns of it. The area is not going to change. We're just going to keep it as a square the whole time, so that won't change. Our orientation is not going to change. The field and the area vector are going to be in the same direction. But we're going to change the field. It's going to go from 0 to something, 0.5 Tesla, in 0.8 seconds. So our field is changing. So we're going to have an EMF equal to a negative number of turns, change in flux over change in time, but the area is not changing, so I can take that out of the delta, and our orientation is not changing, so it's going to be cosine 0 all the time. So now our EMF is a negative number of turns, area, change in field per change in time. That'll be negative 200 turns. The area of the square loop is going to be 0.18 meters times 0.18 meters for the area of a square. And then our final magnetic field is 0.5 Tesla. Our initial was 0, so our change is going to be 0.5 in a change of time of 0.8 seconds. This will give us an EMF of a negative 4.1 volts. Don't worry about the negative right now. We're just interested in the magnitude of this EMF that's been induced. We're going to get the direction of the current in just a moment. So the magnitude of the current is going to be equal to the EMF divided by the resistance of this coil. And that's going to be 4.1 volts over 2 ohms, 2.05 amps. What about the direction of this current? Good question. Well, if we're looking at this coil, and as we have indicated, the B field is going into the page away from you as you're looking at it. So that's the direction of our flux. We have a flux that's going into the page. It's going from nothing, 0, to something, 0.5 Tesla, in 0.8 seconds. So it's increasing into the page away from you. If nature can do it, it's going to try to maintain the status quo. So it will create its own flux out of the page towards you in order to try to mitigate this increase into the page. So it will increase its own flux out of the page. That requires a current to flow counterclockwise through the loop as you're looking at it. So this current will be counterclockwise as it's setting up its own induced magnetic field out of the page towards you to offset the increase in magnetic field that's going into the page. And that would be our induced current. Let's focus on this Lenz's law. It's a pretty neat law, that negative sign, but it really means a lot. And we need to understand it a little bit to understand this phenomena and maybe nature in general. The polarity of the induced EMF is such that it tends to produce a current that will create a magnetic flux to oppose the change in magnetic flux through the loop. In other words, it's going to just oppose the change. It's the negative sign. To find the current direction using Lenz's law, I'm going to suggest that you ask the following 4 questions in the following order, the following hierarchy of questions. I'm not sure this would be found in your book, but this is the way to approach the thinking concerning Lenz's law. First question is, in what direction is the flux through the loop? What is your original direction of the flux through the loop? And that direction will always be the direction of your magnetic field. So whatever your original magnetic field direction is, that's the direction of your flux. As you proceed through the problem, is that flux increasing or decreasing? You're going to have to ask yourself that as the problem proceeds. What's going on there? So you know the direction of your flux. Is it increasing or decreasing in that direction? Once you determine what's going on, then you're ready to ask what's going to be the reaction to that. Question 3, in what direction is the induced magnetic field to oppose this increase or decrease? And then finally, by the right-hand rule, what is the direction of the induced current needed to create the induced magnetic field? Let's take a look at an example. We're going to drop a bar magnet through this wire loop. And this wire loop is in the horizontal plane like this with this resistor closest to you. And we're going to drop this bar magnet down and let it fall through this loop as it's falling down. The south end of the magnet is toward the loop as it's falling, and the magnet's getting closer and closer to the loop as it's falling down. While it's falling and coming closer to the loop, in what direction is the induced current flowing through that resistor? Is it right to left or left to right? Well, we need to go through the hierarchy of questions, and our first question is, what's the direction of the original magnetic field? We have ourselves a magnet here, and as we're looking at this magnet falling, we have a north pole up here and a south pole down here. Field lines come out of the north pole and they go into the south pole. So as this thing is falling, we have field lines that are going up into the south pole. As far as that coil is concerned, there are field lines going upward into the south pole of the magnet. So the direction of our original flux is actually upward into that south pole. All right, what's the second question? Well, as we proceed through this problem, is that flux increasing or decreasing? This thing is falling, and our flux lines away from the pole are spread out, but as you get closer to the pole, they get pretty dense. So as this thing falls towards this coil, we have a flux that's going up, and it's getting stronger as we get closer to the pole of the magnet. So this flux is increasing as the pole of the magnet gets closer to the coil. So we have a flux that's going up, and it's increasing. What is nature going to do about that? So we're ready for the reaction. What is the direction of the induced magnetic field? Well, the coil is encountering a flux that's going up and increasing, So nature's response is to create a magnetic field in the opposite direction, going down. So the induced magnetic field has to be down, opposing the increase in flux going up. And what direction would the current need to be in order to create that magnetic field going down? It has to be going around like this. Around like this as you're looking at it, which would mean it would be going right to left through that resistor that's closest to you. So by the right-hand rule, the induced current is going right to left through that current resistor as it is closer to you on that coil. All right, we're going to let that magnet fall all the way through. And once it's on the other side and continues to fall, the question now is, what is the direction of the induced current through that resistor now? We have the coil up here with the resistor closest to you, and it's falling through, and this continues to fall like this. Okay, again, we want to go through that hierarchy of questions, and the first question is, what is the direction of the flux through that coil? Well, the north pole is facing up, and the flux lines are facing up like this. So again, in this case, the flux lines are going up through that coil. So our answer to the first question is we have flux lines going up. That's the direction of our flux. As this magnet continues to drop, is that flux increasing or decreasing? Well, the pole is getting further away from the coil, so we're getting more spread out lines. In fact, some of those lines aren't going through the coil anymore. So the flux is decreasing as this magnet continues to drop. So we have a flux that's going up and it's decreasing. Nature is going to react to that. What direction is the induced field? Well, nature is going to try to maintain the status quo. I always say nature. If we went into the science of this, we'd have to look into the fabric of space-time and the change in energy associated with these fields, and that's how nature reacts to this. Just like in any other natural process where nature opposes change, there's really a lot of science involved. So it's not like a supernatural thing necessarily. It is science involved in this reaction to the change. So in this case, we have a flux that's going up, it's decreasing. Nature's response is to create its own magnetic field in the up direction, opposing the decrease in flux in that direction. And that would require a current that is flowing left to right through that resistor that's closest to you by the right-hand rule. So by the right-hand rule, we're going left to right through that resistor. In general, if you're asking these questions and you've determined your flux direction by the first question, the second question is increasing or decreasing. If you say for the second question, if that is decreasing, then the answer to your third question will always be exactly the same direction as the answer to your first question. If your second question is decreasing, nature is going to go in the same direction as the original flux. If the answer to your second question is increasing, then the answer to your third question is going to be 180 degrees opposite the answer to your first question. It's going to be, nature is going to exactly oppose the increase in flux of the first question. All right, let's try another example. What is the direction of the current induced in the resistor when the current in this long straight wire decreases rapidly to zero? So I have a current flowing. As you're looking at it, I always have to think about how you're looking at it. It's flowing right to left. And if you were to point your thumb in the direction of that current, right to left, you would find that your fingers are going into the page in the vicinity of this coil. So the direction of the original flux is indeed into the page by the right-hand rule for infinitely long wires. What's happening though over the course of this problem? Well, the current is decreasing rapidly to zero. We know the B field due to a wire is mu naught I over 2 pi r, so it's proportional to the current. So if the current is decreasing rapidly, so is the magnetic field, and so is the flux. So we have a flux that's going into the page, and as you're looking at it, and decreasing. What's nature going to do about that? Well, as I just told you, if your answer to the second one is decreasing, then your answer to the third question is going to be, we're going to have an induced field into the page, exactly the same direction as the original field. And so our induced field should be into the page to oppose the decrease in flux in that direction, and that would require a current that is flowing clockwise through this coil. Hence it's going left to right through that top resistor. So we have a current that's flowing clockwise through this coil, left to right through that resistor, and that would be our induced current in this coil by Lenz's law. Let's try this one. We have a voltage, an EMF, a battery, and we have a switch. We have a coil looking like a solenoid. We have a secondary coil around that solenoid with a resistor on top. In which direction, when I close the switch, is the current going to flow through that resistor as you're looking at it? Well, if I close the switch, what's going to happen? We're going to have, as we see it, a positive current flowing out of that battery. It's going to flow in a forward direction, upward, through the front coil around that solenoid. So all of our currents are going to be flowing upward through the turns of this solenoid, like this, and that will create a magnetic field that is going, as you're looking at it, right to left. So all of a sudden, when we close that switch, we're going to go from zero magnetic field to some finite magnetic field, right to left through that coil. And that secondary coil is going to feel the same thing. So it's going to feel an increasing flux that's going right to left. Nature will oppose that and set up its own field, left to right, through that coil, a secondary coil. To do that would require a current that is flowing, as you're looking at it, left to right through that resistor. So the current through that secondary resistor, secondary coil, will be left to right. There's no electrical contact here. It's all by induction that we're inducing a current to flow. It's the idea of generating power. Let's try yet another example, this one with Faraday's law. The flexible loop at left has a radius of 12 centimeters and is in a magnetic field of strength 0.15 Tesla. The loop is grasped at points A and B and squeezed until it closes. So we're just going to close this loop, do nothing else. We just have a loop in a magnetic field and we're closing it. If it takes 0.2 seconds to close the loop, find the magnitude of the average induced EMF in the loop during this time. So just closing a loop in a magnetic field evidently is going to induce a voltage, an EMF, because in this case we have a constant magnetic field, so that's not changing. Our orientation is not changing, but our area is going from the area of a circle to 0. That's changing. By Faraday's law, the EMF will equal a negative number of turns, change in flux over change in time. Our field is constant, so we can take that out of the delta. So we have negative number of turns, field, change in area over change in time. In this case, we only have one turn. We just have one loop. The field is 0.15 Tesla. Our final area is going to be 0 as we pull this taut. Our initial area is pi r squared. The radius of the circle is 0.12 meters. So we'll have 0 minus our initial area over 0.2 seconds. This will give us a voltage of 3.39 times 10 to the minus 2 volts. By just closing this loop in a magnetic field, we will generate a voltage, and if there's a resistance in that loop, we will generate a current. In what direction does the current in the loop flow as we're closing this loop? Good question. Well, we're going to ask those questions. First question is, what is the direction of the flux? Well, it's going into the page away from you. Second question, as we proceed through this problem, is that flux increasing or decreasing? Well, the flux is into the page, and the flux is the number of lines that are going through this loop. The loop is closing, so we're having less lines going through this loop as we close this loop. So the flux is decreasing into the page as we proceed through the problem. What's nature going to do about that? It's going to create its own flux out of the page, into the page, to supplement the decrease. It wants to maintain the status quo, so it's going to supplement the decrease. It's going to be in the same direction as the original field, and that would require a current that is flowing clockwise through this loop. So flux is into the page, it is decreasing. The induced field is into the page as opposed to the decrease. The induced current will be clockwise through the loop as we're closing this loop. Here's a real-world application, a ground fault interrupter. Consider this. You have current flowing into a house, and you also have return current flowing out of a house. And it's going through a iron circle, iron tab there. And then there's a secondary coil around that iron that goes into a breaker circuit. Usually the net current through the coil is 0 because you have as much current going into the house as you have current going out of the house, and you have a certain amount of flux associated with that, probably a net flux of pretty close to 0, flowing through this iron core. But what happens if there's a short inside the house? Let's say somehow a toaster has fallen into the bathtub, and somehow there's a short of electricity going to ground, and hence that electricity that normally is returning through this return wire is now being shorted to ground somewhere and never returns. So all of a sudden the flux of magnetic flux that you had going around these wires is going to change because your return current has suddenly gone to 0, and now you have some kind of finite flux flowing through this iron core. It's gone from 0 to something, and that will induce a current to flow in this secondary coil here. And as that current flows, it goes back into the circuit breaker and shuts off the circuit. So and it happens almost immediately. As soon as there's no return current, the circuit breaker shuts off the current going to the house, and hopefully, if you were in the bathtub, hopefully nobody's hurt. Hopefully that's done so quickly that the circuit has been shut off before any damage has been done. Here are two other devices utilizing induction. If we have a flashlight like this with a magnet going through a coil, we can induce current to flow and store that in a capacitor, and hence we have ourselves a flashlight for emergency situations. Or this kind of flashlight, same kind of idea, where I can generate mechanical energy to generate the movement of the coil and generate light that way. Just make sure if you're going to utilize this in a safety situation that you have eaten enough during the day so that you have enough physical energy to keep this light going, because you can't get something for nothing. Energy has to come from somewhere. It's coming from you to generate this electricity. That concludes the first lecture in Chapter 31, and we will continue on in motional EMF and power generation in the second letter.